Welcome back. Now we're going to talk about double integrals over general regions. So before, in the previous section, we were mapping a rectangle, a nice rectangle up onto our surface, right? And so it was easy for us to map a rectangle because we've got nice straight bounds with regard to my x and y values. But now we're going to begin to talk about general regions. So the idea here is we might have some surface up in space, and instead of having a rectangular shaped region R, we have some bulbous shaped region R. And so when we are trying to find left and right, or upper and lower for my x's and y's, it's going to be a little bit more confusing because we're actually going to have curves or functions. Not everything will be a constant. Here we were able to find two constant x values, a and b, and then two constant y values, c and d. And that's no longer going to be the case. So we have two types of regions. We have two situations. Type 1, if we think about our region, we may have x equals a to x equals b, but we could have curves bounding those. So here we have y, some function g sub 1 of x, and y, some function g sub 2 of x. So instead of having a perfect rectangle, my region now has two vertical bounds defined by that a and b value, and then a curve, y in terms of x. So we've got functions bounding above and below. The other situation that might occur would be type 2, and you can probably figure out what I'm going to draw here. But in this situation, we might have a C and a D, and then my left and right bounds, left and right, could be some weird curve. So I've got C and D, and then I have these curves. Here I have a function x equals h sub 1 of y, it's hard to think about that backwards, h equals x sub 1 of y, and then some x equals h sub 2 of y. All right, so we've got some different kinds of regions, and that's going to change our bounds a little bit. So we have a stronger theorem basically for Fubini's. So previously we defined Fubini's and my bounds were a and b, c and d. Every value for x and y, upper and lower, was a constant. So now we're going to rewrite it, and we're going to have some variable functions inside. So just reconsidering what we're doing before we introduce that theorem, our region R is now no longer rectangular. So when we break it up into all of these smaller rectangular areas, and then we're going to calculate that height off of that point. So extruding this dot out of the screen towards you, that's going to give you your height. So you can find the volume of all of those parallelepipeds. And you see this isn't as accurate until we get those rectangular sub-regions that we've partitioned off inside this big sort of egg-shaped region, infinitely small. So again, building towards finding that volume, it is the limit of all of these sums. So we have some height, some f of xy, right? This height of the parallelepiped, and then times that base area, and the base area is found by some a and b bounds on x, or c and d bounds on y, right? So that's what we have been talking about. And the only thing that differs now is instead of these bounds being constants, we could have a function representing one of our boundaries. So my stronger form for Fubini's theorem says that if I have a multivariable function which is continuous on my region R, and so formerly the region R was a rectangle, but now that region R may have two vertical bounds or two straight bounds, constant bounds extending off the x-axis, and then some variable function bounds extending out of the y-axis. As long as those g sub 1 and g sub 2, those functions bounding my y, are continuous throughout my horizontal xy interval, a to b interval on x, then we set it up like this. Since y is variable, those are going to go on the inside, integrate with respect to y. So we've got y equals g sub 1, y equals g sub 2, and then my x's are constants, a to b. And the only thing that differs here is we can reverse this. We just use h sub 1 and h sub 2 to represent my variable bounds for x. And then y, we use c and d for my constant values for my interval on y. So if we look at this picture here, this represents our first situation where A and B are straight lines, constant lines, extruding off of the x-axis parallel to the y-axis. And then my other bounds in terms of y, those are curves. Y sub 1 is a function of g sub 1. It's closer to the origin. Y sub 2 is a function of g sub 2, which is further from that origin off the y-axis. So this was part 1, and we'll look at part 2. So for part 2 here, C and D are constant. Those are straight lines. And then my bounds coming off the x-axis, I have x being a function. H sub 1 is closer into the origin. H sub 2 is further out. So we've got like inner and outer. Here we have left and right. So left is outer minus right inner. Here we've got this outer in the front, inner closer towards that y-axis. So I'm going to encourage you to pause your video and just think about how this setup is occurring, right? We have these two rules here that we want to understand. The main thing you want to keep in mind is that we're always going to put those constants last, all right? And so before, when we could switch dx and dy, that made our lives easy. We're not going to want to do that anymore. All right, so whichever one is constants, those are going to be the ones that we integrate last. So for this example, we're going to evaluate this double integral for the surface, z equals x plus 2y, over the region D. And D is bounded by these two parabolas. So the first thing we always want to do is draw a picture of our region. Normally we call it R. Here we're calling it D. A variable is a variable as long as you know what it means. So this D is taking place of what we formerly have used as R. So these are both two parabolas opening up. Y equals 2x squared opens up. It's stretched vertically twice as tall. So there we've got y equals 2x squared. And then we also have y equals 1 plus x, which is a parabola opening up. It's going to be a little wider than this and has a y-intercept of positive 1. So there's y equals 1 plus x. Now, what we want to notice is we know these 2 points where they're intersecting. We can calculate those 2 points, and that's going to be at -1 and +1. So my region is the area between these two curves. I have constants on my x-axis, And on my y-axis, I'm bounded by curves. So I have an above, an upper bound, and a below, a lower bound is going to be 2x squared. So I know we have these two types from the previous screen from our definition. And I'm not saying you need to memorize them. You want to think about what your bounds are and which integration is it going to be easier to perform first. Should we integrate with respect to y or with respect to x first? All right. So when we look at this, I don't want to integrate from left to right. I don't want to say, well, this function minus this function. Or up here, we would have two different bounds from left to right. So I hope you guys can see what I'm saying. The bounds change. Up here, left to right, right to left. That's kind of a pain. Whereas if we think about it vertically, we have an upper and a lower, right? So I've got this function and this function as my bounds. So when I set up my volume, I've got -1 to +1. X equals -1, X equals +1. You don't have to write the X equals there, but I think, especially when we're learning, it helps us to always remind ourselves what these variables mean. And then my Y bounds. So I have a upper bound and a lower bound. My upper bound is y equals 1 plus x, and my lower bound is y equals 2x squared. I'm realizing I wrote 1 plus x, but that's 1 plus x squared. I graphed it right. I left this square off here. So I graphed what I wanted, but when I wrote it, I didn't write the square. So my integrand is x plus 2y. And then I'm going to have, since these are functions y in terms of x, I'm going to have dy then dx. So take a minute, pause, make sure you understand or you know how I set this up, because that is what's important. And also, always remember your constants, those are going to be on the outer integral. You're going to be integrating with respect to those second. Okay, so the outside, we deal with that second. We're going to use this inside here first. All right, so let's set this up or start working on this. I have v equals the integral from -1 to 1. Now, I'm integrating with respect to y. That means x is a constant. So I have xy for the first term, integrating 2y, that gives me y squared. And my functions that I'm plugging in, I've got y equals 1 plus x squared. I'm going to use a color here. Y equals 2x squared. And I still have my dx. So these guys, remember, these are both in terms of x. If it helps you to write the variable below the integral so you know what you're dealing with. Now, we have to plug this function in for both of these y's, this function in for both of these y's, what that would look like. Got my integral. These are x's from 1 to 1. So I have x, 1 plus x squared, plus 1 plus x squared quantity squared minus x times 2x squared plus 2x squared squared. And unfortunately, you just have to do this algebra here. All right, so you need to be able to distribute, FOIL, multiply those, distribute that negative. I'm going to go ahead, pause the video, jump to the next step, but you should make sure you can get what I get on my screen. So everybody paused, now you're unpaused, you did all of this algebra, and you get this for your integrand. Negative 3x to the fourth minus x cubed plus 2x squared plus x plus 1. And we're going to integrate that with respect to x. So skipped the busy work. And working through this, I'm going to get negative 3/5 x to the fifth minus 1/4 x to the fourth plus 2/3 x cubed plus 1/2 x squared plus x. Now we need to plug in 1 and negative 1. And again, I know you can plug 1 in for all these values and then plug negative 1 in for all these values and subtract those two numbers. So we end up with 32 over 15. Make sure you can get that value on your own, but I'm not going to sit here and talk you through it in the video because that is basic algebra at this point. If you have any questions, feel free to email me. I hope this makes a little bit more sense about how we are determining our bounds and setting this up. Good luck out in the real world.